So next we have 16th group elements. So in this 16th group element, the main important elements are oxygen and sulfur. These two are very important, and we have to know about the allotropes of oxygens. Those are means O2 and ozone. Molecular oxygen and ozone are the allotropes of oxygen. And next we have to remember melting point order, boiling point order also. Both are same only. I explained in 15 group element this concept. So H2O will be having more, then H2PE, sorry, H2 polonium, and tellurium, and H2 selenium, at last H2S. So this I have explained in 15th group element. So if you have not seen that video, please watch that video, then it will be clear why generally in the groups from top to bottom boiling points increases, but here in this case it will not happen in case of oxygen and nitrogen and fluorine groups. Okay, so I have explained there, and we directly go to the molecular oxygen. So in the molecular oxygen also we have like first we talk about MOT of oxygen. I am not going into the details because MOT of oxygen is well known, so I will tell only few things. Like here we have two two states. We have a triplet state and as well as a singlet state. And for triplet state, the term symbol will be this one, and for singlet state, two term symbols are possible. So this is the one term symbol, and this is the another term symbol. Okay, for for triplet state we have two term symbol, sorry, one term symbol. That is, this is possible when the 15th electron and 16th electrons occupies the 2px pi and pi 2py orbitals, I think anti-bonding orbitals. Okay, in that case it's possible. And when this is possible means like so both the electrons in the pi 2px star and pi 2py star occupies two different orbitals with opposite spin. So this is the singlet state. So for this it's possible, and in this case it's possible when so both the electrons occupies the same orbitals. Okay, in that case this term is possible. Okay, so now here what we need to remember that this term symbol is electrophilic in nature. So why this is electrophilic in nature? Because as we can see here, we have one vacant orbital here. So because of that, this is electrophilic in nature. Now the most of the reactions, if we see we have three term symbols. So if we see the energy orders, triplet will be the least energy, then 1 del G, and higher energy will be this one. So this is the energy order. Okay, so we know that higher the energy, that will be having a means unstable, it will be in the higher energy side. This is 1 del G and this is 3 sigma Z negative. Okay, so for oxygen molecule, this is the ground state and this is the excited state. Okay, now the most of the reactions for oxygen takes place from this term only, because this high energy less stable, and this is also having high energy, but this is having reasonably more lifetime. Okay, so initially the electrons can go from here to here and it spends some time here. Since it's unstable, in this state it's unstable, and it will come back to the this term, and the reactions will take place from this place. And it's possible to synthesize this del G term photochemically also, like through the energy transfer. through energy transfer it's possible to synthesize. Like we can take ruthenium bipyridine thrice 2 plus, and this we treat with a triplet oxygen, and there is a, so here we can generate a singlet state from a triplet state by the photosensitization method. So in the photosensitization method, what will happen is the energy transfer will takes place from the, we can generate a singlet state from the triplet state by treating with the ruthenium bipyridine complex through the energy transfer, that means a photosensitization method. Okay, so this is the one way where we can prepare the singlet state of oxygen from the triplet state, and we can also prepare by using another method, so where we can use phosphorus trialkoxy compound. This compound upon treatment with ozone, so we will get a ozonated compound like this, and we know that phosphorus is having high tendency for the formation of bond with the oxygen, and this is another way where we can generate a oxygen which is having a singlet or del G as a Tom symbol. So why I am explaining this one means, like in examination they may ask for which state most of the reactions takes place in case of oxygen, so that time we have to choose this option. And this also involves in the Diels-Alder reaction. This singlet oxygen also can involve in the Diels-Alder reaction like this. So here we get this compound. And then we'll go for ozone. Oxygen is done. Now we'll go for ozone. So what is the hybridization of we can say that, what is the shape of ozone, we can say, and this is having a angular shape, and this also comes under CTB point group, and these things, just it's not that important about ozone, but just these two things we remember, and that much is sufficient. And then about sulfur, only some few compounds are there, those things are important. And another important thing is hydrogen peroxide. Okay, so hydrogen peroxide can act as a oxidizing agent as well as reducing agent, so these reactions are very, very important. Okay, so in the both the cases, H2O2 plus, this is the acidic medium, and H2O2 plus 2OH minus, this is a basic medium. In the both the cases we take 2 moles of cerium 3 plus. So in the acidic medium it acts as an oxidizing agent, in the basic medium it acts as a reducing agent. So what is the oxidizing agent means? Oxidizing agent means this itself get reduced and it oxidizes others, and here cerium plus 3 is the oxidation state. Here we get a cerium plus 4 plus 2H2O. So in this reaction, what is the role of cerium? Because cerium is getting oxidation and it's reducing others. Okay, here cerium is a reducing agent. See, oxidizing agent means it get reduces and it oxidizes others. Reducing agent means it oxidizes itself and it reduces others. Here cerium is plus 3 and here plus 4. So it oxidized and it reduced H2O2. So that's why this is acting as a reducing agent here, and this act as a oxidizing agent. And similarly here, this is in the basic medium, it has to act as an oxidizing agent. So oxidizing agent means it should lose some of the, means like it has to give some electrons to the cerium. This cerium plus 4, sorry, and this gets converted to cerium plus 3 plus 2 moles of water plus O2. So these 2 points are very important. H2O2 in oxidizing agent, it acts as a acid, sorry, in acidic medium it acts as an oxidizing agent. In the basic medium it acts as a reducing agent. And what about H2O2 and water, which is a strong acid? So H2O2 is a strong acid compared to the water. So generally when we see a H2O2 bottle, so generally we store the H2O2 in the plastic bottle, but we will not store in the glass bottle like that. So the reason why we are storing in a plastic bottle, because so when this H2O2 get exposed to the air, or when it get we can say it's unstable. H2O2 is unstable. This undergoes disproportionation reaction. So what is the disproportionation reaction? The H2O2 gets converts into H2O plus oxygen. Okay, so this reaction is explosive in nature. So when when we open the since it's unstable, if we open the cap of this bottle, this may undergo disproportionation reaction. If it is in the some glass, some glass may broke, so that's why H2O2 will store in the plastic bottle. And this reaction also remember. So for H2O2, these are the 3 things we need to remember. And then there is one reaction called Penton reaction. No need to go in the detail. Penton reaction. What is the Penton reaction? A decomposition of H2O2. Decomposition of H2O2 into water plus oxygen. So this is called as a Penton reaction. Just remember one statement. It's not that important. And then we'll go for this is about the oxygen and ozone. And then we have these. So next important one is oxyacids of sulfur. And here we have 4 compounds: S2O3 minus 2, S2O4 minus 2, S2O5 minus 2, S2O6 minus 2. And I will tell how to remember this, because if they give the structure, if they give the formula, and if they ask the structure, and if they ask any questions about the structure, it's very easy to predict, and it's very easy to answer also. If they give the name, then it's difficult. Okay, so from the structure we can make out the name. So this structure looks like this: O, O, O. Okay, and this we call it as a thiosulfate. And why we call it as a thiosulfate, and I will explain later. And here S2O4 structure looks like this. This is S2O4, and this we call it as a dithionite. And why we call this one as a thiosulfate? Because here we have a SS bond, and here also we have SS bond, but we are not calling this one as a thiopionate. We are calling it as a dithionate, because here both the sulfur atoms are the central atoms, but here this is not a central atom. Okay, because of that we are calling this one as a thiosulfate, and we are calling this one as a dithionate. And we'll go for S2O6 now. O, O. Just remember that. So this is having a here tetrahedral shape, and this also just remember, means just to, in order to remember, I'm telling this, so like that also you can remember. So here also each sulfur is having tetrahedral shape. Okay, so whichever having tetrahedral shape, those prefix will be 8, which we don't, means here this is not having tetrahedral shape, so the prefix is height here. For this also, one sulfur is having 3 oxygens, another sulfur is having 2 oxygens, so this we call it as a disulfite, and this is a dithionate. So this is very simple to remember these names. So first point is, which is having sp3 tetrahedral shape, the prefix will be 8. Which is not having tetrahedral shape, the prefix will be 8. Okay, and then so this is clear, we call this thiosulfate. Why? Because ss bond is there. And the second one, fourth one, see, we are calling this one as a thia, because here in the both the cases sulfur is in a equilibrium environment, but here sulfur is not in equilibrium environment, so that's why we call it as a disulfite. So don't get confused, so just remember that first one, second one, third one, fourth one. Okay, remember like this, ST. Okay, S means sulfate, T means thionate, S means sulfite, T means thionate. Okay, this is clear. Now if it is a tetrahedral shape, the prefix will be 8, and this is also prefix will be 8, and this will be 8. Okay, and in except here remaining all places di. Okay, so see, dithionite, disulfite, dithionate. Okay, this one is thiosulfate, so these are the 4 compounds. So they may ask that this kind of examples they may ask, because here sulfur is not in the equilibrium environment, and this is important and this is also important. Okay, like this you can remember. I hope it's clear. Just remember that this sequence ST. Okay, S means sulfate, means like, since in the first case it is a tetrahedral shape, prefix 8 is coming, last one also prefix 8 is coming, this is 8 and this is 8, so this is thia, and this is di, and this will be S2O3 minus 2, S2O4 minus 2, just increase one oxygen, S2O4 minus S2O5, S2O6 minus 2. This is thiosulfate, dithionite, disulfite, dithionate. So these are the oxyacids of sulfurs, and we have few more, 8 more we have. So these are easy to remember, but those are little difficult, but we have to practice more to remember. First I will write all the names. We start from sulfuric acid. Second one is peroxo monosulfuric acid. Third one is sulfuric acid. Fourth one is dithionous acid. Fifth one bisulfurous. Sixth one dithionic. Seventh disulfuric acid. This is also called as pyrosulfuric acid. Last one is peroxo by sulfuric acid. So for maximum 4 to 5 I can tell how to remember. So remaining 3 you have to by heart it. So we know that H2SO4, sulfuric acid, we know H2SO4. Okay, now for this we start from the H2SO4. okay, now increase one oxygen, that will be H2SO5. okay, this is the second one. And thiosulfuric acid means H2S2O3, and here H2S2O4, then H2S2O5, H2S2O6, H2S2O7, H2S2O8. okay, so this is clear why we are calling it as a monosulfuric acid, because if we see this structure it will be like this: S, oxygen, oxygen, here one OH bond will be there, and here the peroxy bond will be there. So this is the H2SO4 structure. So here we have peroxy bond, and it's like sulfuric acid only, instead of like we just increased one oxygen. okay, but it's more or less it's like sulfuric acid, so we call it as a peroxo. This is peroxo monosulfuric acid. Next, here H2S2O5, sorry, H2S2O3. so what is H2SO4? Sulfuric acid, and here just one oxygen is replaced by one sulfur. That's why, so before also when when I was saying this compound, this we call it as a thia compound, because there is a thia bond is there. okay, and here H2S2O3, if we see the structure, the structure will be like this. Yes, this will be the structure. So here also we have a thia, so that's why this is a H2SO4, instead of one oxygen one sulfur is there, so we call it as a thiosulfuric acid. okay, next, the 4 and 6 is same, only prefix is changing. Here us, here ik. okay, and 5 and 7 also same, because here also us, here ik is ik. And 8th one we have to remember, here there is a one peroxy bond will be there like this. Like this, one peroxy bond will be there. So if you if you can, the what you will do, if they ask anything in this 8, just write in this sequence. First start with sulfuric acid and peroxo monosulfuric acid, thiosulfuric acid. So these 3 is very easy to remember. okay, the 4th one will be diethionous, and the 6th one will be just prefix will be changing, diethionic, us and ik. And 5th and 7th is also same, bisulfurous acid, here disulfuric acid, or we call it as a pyrosulfuric acid. This is very very important, this we call it as a oleum also. So H2S2O7 we call it as oleum. So this is disulfuric acid, or we can also call it as a pyrosulfuric acid. And I used to remember these things like this. So like, if you like this one you can remember this way, or if you have your own ways, that also fine. And then we have like H2SO4 synthesis also very important. So one process is there, that is a contact process. In that process we can synthesize H2SO4. So to synthesize H2SO4, the first step will be treatment of sulfur with oxygen. It forms SO2. This is the first step. This further we treat with oxygen. it forms SO3, and this one we pass it through like we pass through the V2O5 silica beads. So this is the catalyst here. Vanadium oxide is the catalyst in the synthesis of H2SO4. Okay, and after passing, we clean this one with oleum. I just now explained H2S2 H2S2O7. So the finally we'll get H2SO4. And here in this process, what things we need to remember is the catalyst is very important, and with what we are washing, the volume is very important. And then this also requires high temperatures and high pressures. So why it requires high temperature and high pressures? So I have explained in the 15th group elements. There I have explained that the end is inert because there is a triple bond. So because in a Haber's process we are using high temperatures and high pressures to overcome this inertness. Okay, so oxygen also having O double bond O. So this also strong only. So if you want to break this bond, here also we need to use high energy and high temperature as well as high pressures. So these are the things you need to remember. Then sulfur nitrates are there in this topic only, but I have already made a video on sulfur nitrates, and those are also very important. In this oxygen 16th group element, you definitely get a question from this sulfur nitrates, or if not from sulfur nitrate, it can be either on the structures and before what I said, oxoacids of sulfur. So these are the very important.